Hi, everyone, and thank you very much to the organizers for inviting me to Ultramath 2022. I'm really sorry I couldn't be with everyone there. I'm sure it's going to be a fantastic meeting, but I appreciate the opportunity to at least record this video and share my work with everyone who is in attendance. I'm going to talk today about a work that I did about a year ago where I gave a non-standard proof of the spectral theorem for unbounded self-adjoint operators. But before I explain what that's about, I wanted to give a quick shameless plug. I have a new book coming out this summer called Ultrafilters Throughout Mathematics, which I think the audience of this conference might find interesting. Besides discussing foundational issues about ultrafilters and ultraproducts, I describe a wide variety of applications of ultrafilters and ultraproducts throughout many different areas of mathematics. So I hope you get a chance to check it out and maybe share it with your colleagues and your students. Okay, so on to the main purpose of the talk. Before I get on to the general version of the spectral theorem, I thought I would describe the finite dimensional version that many of us teach our undergraduate students and will turn out to be, using the non-standard approach, the only real standard fact that one needs to assume in order to deduce the version for unbounded self-adjoint operators. So the finite dimensional version of the spectral theorem says if you have a finite dimensional Hilbert space H, and in this talk, all Hilbert spaces are over the complex numbers, and A is a self-adjoint operator on H. So if we're thinking just in terms of H being complex numbers to the n, this would be an n by n matrix whose conjugate transpose is equal to itself. Then the statement says there are finitely many eigenvalues, distinct eigenvalues, lambda 1 through lambda n of H, all of which are real numbers. And so that you can decompose the identity operator as the sum of the projections onto those eigenspaces. And then your operator A is the appropriate linear combination of those orthogonal projections. So it's lambda I pi. Okay. So that's the finite dimensional version of the spectral theorem that hopefully we're all very familiar with. And the general version of the spectral theorem allows one to work with infinite dimensional Hilbert spaces instead of finite dimensional ones. And moreover, allows one to work with unbounded self-adjoint operators. And I'll define exactly what those are later. But in order to state and prove such a theorem, these finite sums that one sees here have to get replaced by certain integrals that we will also define shortly. So here's what the spectral theorem looks like in this more general case. So suppose that A is an unbounded self-adjoint operator on the Hilbert space H, and again, I'll define that shortly. Then there is a projection valued measure, P, from the Borel subsets of R to bounded operators on H, such that you can decompose your operator A as the integral of the reals of the identity function with respect to this projection valued measure. And again, I will define what that integral looks like precisely in a second. But this is the appropriate generalization of the previous finite dimensional version to this most general setting. And this most general setting isn't just generalization for the sake of generalization. It's actually extremely important, for example, in quantum mechanics, because when you're discussing measuring observables with continuous spectra like position and momentum, in order to get probability distributions, what's the probability that the position of this particle will be in this open set? One has to use this projection valued measure in order to explain that probability distribution for a given state of the system. Okay, so this is of fundamental importance in quantum mechanics. It's also used in von Neumann algebra theory. It's truly a very important theorem. So in this talk, I'm going to describe a non-standard approach to the proof. The standard proof, in my opinion, has two major drawbacks. So the first drawback is that you have to quote the spectral theorem for bounded normal operators. So bounded operators it's a step up in complexity from the finite dimensional version. So we're now talking about infinite dimensional Hilbert spaces, but bounded operators. And then, unfortunately, you're not quoting the spectral theorem for bounded self-adjoint operators. You have to quote it for the larger class of bounded normal operators. And in order to make that reduction, you have to use this thing called the Cayley transform. And I find the whole thing kind of difficult to motivate and a little awkward. And this is very much how it's proven in most textbooks. So in this talk, I'm going to outline a proof using the well-known non-standard technique of hyperfinite approximation, which will then allow us to just assume that the theorem holds in the finite dimensional case, which is the easy case that I mentioned at the beginning of the talk and that we teach to our undergraduate students. Okay, so I don't need to quote any bounded normal case. I can go straight to the finite dimensional case. And the proof is based on the notion of the non-standard hull of an unbounded self-adjoint operator, which Rob introduced in his paper attempting to give a non-standard approach to quantum mechanics. And in some sense, the majority of what I'm going to present here in this talk is present in that paper, but in my opinion, that paper left a lot of details out, and those details aren't entirely obvious to me. So one of the things that I did in my paper was to flesh out the exposition of Rob's approach in more detail. And I should say there is a non-standard proof of the spectral theorem for bounded self-adjoint operators Moore gave in the 1970s. And although it doesn't look exactly the same morally, it basically is a special case of the proof that I'm going to present here. Okay, so let's describe some preliminaries about unbounded operators, self-adjoint unbounded operators, projection valued measures, etc. So all an unbounded operator on a Hilbert space H is, it's a linear operator, but it may not be defined on all of H. It's only assumed to be defined on a dense subspace of H, and that's called the domain of. We'll be talking about extensions of unbounded operators. So I'll say an unbounded operator B on H is an extension of some unbounded operator A if just as functions, B is an extension of A. In other words, A is the restriction of B to its domain. And we'll actually need this terminology in the case when I have a big Hilbert space K, a closed subspace of it H. A will be an unbounded operator on H, and B will be an unbounded operator on K, and B will be an extension of A. We'll use the same terminology. Okay, so in order to describe self-adjoint operators, we need to describe adjoints of unbounded operators. So if A is an unbounded operator, we define the adjoint of A, excuse me, to be a linear operator, A star, which is defined as follows. So first of all, I have to tell you what its domain is. So the domain is all vectors X in the Hilbert space, for which when you look at the map from the domain of A to the complex numbers, which sends Y to the inner product of X with AY, that should be a bounded map. So an absolute value, that should be at most K times the norm of Y for every Y, where K is some bound. Okay, and then if X is in the domain of A star, then we define A star of X to be the unique element of H for which the equation A star XY equals XAY holds for all Y. And that is guaranteed to exist by the Rees representation there. Now, unfortunately, it's not always true that this operator A star we've defined is an unbounded one, meaning its domain is dense. This happens precisely when A is so-called closable, meaning if I take the graph of A and take its closure, then the resulting set is the graph of an unbounded operator. And for the operators we're going to talk about in this talk, the symmetric and the self-adjoint ones, this always happens. So A star will in fact be an unbounded operator again. Okay, so an unbounded operator is said to be self-adjoint if, well, no surprise here, it equals its adjoint as unbounded operators. So that includes the assumption that they have the same domain. A weaker notion is for an unbounded operator to be symmetric, and that just means that you can slide A across the inner product, right? So AXY equals XAY for all X and Y in the domain of A. Another way of saying that is that A is symmetric precisely when A star is an extension of A. And if you phrase it that way, you see that self-adjoint operators are symmetric, and unfortunately the converse is false in general. And in order to get the nice properties that you would want a self-adjoint operator to have, mimicking the situation for bounded operators, the definition given in the first bullet point is the correct one. Symmetric operators do not behave the right way. For example, it's not the case that the spectrum of a symmetric operator is contained in the reals. So that's an undesirable property. Another way of saying that a symmetric operator is self-adjoint is that it has the same domain as its adjoint. That turns out to be equivalent. And we'll need a couple basic facts about symmetric and self-adjoint operators. So the first one is, if you have a symmetric operator and its domain happens to be the entire Hilbert space, then in fact, it's necessarily bounded and self-adjoint. And the other fact that we'll need is that self-adjoint operators have no proper symmetric extensions on the same Hilbert space. So they're like maximal symmetric operators. Okay, now I can tell you what a projection valued measure is. So let's fix some measurable space XB. Then a projection valued measure on XB, well, it's like a measure, except the sets in the sigma algebra B aren't going to get assigned real valued measures. They're going to get assigned, as the name indicates, projection valued measures, where the projections are coming from some Hilbert space H. Okay, so that's what the first bullet point says. For every measurable set omega, P of omega is a projection on H, and to make the notation a little nicer, we might write P sub omega instead of P of omega. Just like the measure of the empty set should be 0 and the whole space 1, if we're thinking of a probability space, here the measure of the empty set, what projection should that be? That should just be the 0 projection. And the measure of the whole space, what projection should that be? It should be the identity map. And then countable additivity of the measure takes the following form. If I have a collection of pairwise disjoint measurable sets, and I call their union omega, then what does P sub omega do to X? It's the sum of the P sub omega n. Okay. Now, when you have a projection valued measure, you can integrate with respect to them. How does that work? So let's fix such a projection valued measure. The first thing you notice is that you get ordinary complex measures from the projection value measure when you fix two vectors, x and y, right? What is the measure, let's say mu x sub y of omega? You just calculate the inner product of y against the projection p sub omega of x. It's a little calculation to show that the total variation of this complex measure is bounded by the product of the norms of the vectors. And if I take the same vector twice, so mu xx, which we simplify the notation and just call it mu x, that's actually a positive measure on x. It's not necessarily a probability measure. It incides the whole space measure the norm of x squared. Okay, so if x is a unit vector, it is actually a probability measure. Okay, so now if I have a measurable function f, I can get an unbounded operator denoted the integral sub x of f dp as follows. So I first have to tell you the domain of this operator, and it's simply the L2 elements of x with respect to this operator. And by that, what I mean is it's all the vectors x in H, so that when I integrate the absolute value of f squared with respect to the measure d mu x, that positive measure, it's finite. Okay, so you can check that that is a dense subspace of H. So if I have an x in that domain, how do I define the operator, which the operator is this integral x FDP? How do I assign its value to x? It's enough to tell you what happens when I when I inner product it against some vector y, and I just want the formula, the integral of x of f with respect to this complex measure d mu xy. That should be the answer. That's an ordinary integral with respect to this complex measure. So it turns out that you can define this operator in this way, and it works as an unbounded operator. And then if x is in the domain, then your function f is actually an L1 function with respect to the absolute value of the measure mu xy, regardless of the y. And then finally, for our purposes, if f is actually a real valued measurable function, then the operator you get is not just an unbounded operator, it's a self-adjoint unbounded operator on H. So it's really this, as far as how you think of this integral is concerned, it's really that formula, inner product y against the integral x f dpx, just being the ordinary integral of f with respect to the measure d mu xy. That's the essential takeaway of how you should think of this operator. Okay, and now we can explain the spectral theorem, at least what it says. So if I have a self-adjoint operator, then a spectral measure for A is a projection valued measure, P, from the Borel subsets of R. It's really going to be supported on the spectrum of A to B of H, so a projection value measure, such that when I calculate this operator, the integral of the identity function, that's a real valued measurable function. So the integral of the identity operator with respect to P, that should give you just the operator A as unbounded operators. So we refer to this equation as the spectral resolution of A. It's not too hard to show if it exists, it's unique. There's a unique such projection value measure. And so what the spectral theorem asserts is that every self-adjoint operator does actually have a spectral measure. The difficulty is constructing the spectral measure. Our main technique for showing that the self-adjoint operator will have a spectral measure is to show that there is an extension of it on a larger Hilbert space for which we know for some reason, namely from transfer, that this larger operator will have a spectral resolution. And then we just want to know that we can restrict that spectral resolution to the original operator and conclude the original operator had a spectral resolution as well. And there's a little proposition here. I couldn't quite find it in the literature, but it's not too hard to prove, which tells you under certain circumstances you can do this. So first, a definition: if I have some Hilbert space curly K and an unbounded self-adjoint operator B on it, and I have a closed subspace H of K, we'll say H is reducing for B if you have this containment of unbounded self-adjoint operators. So the P sub H here denotes the orthogonal projection of K onto H. So this is saying if first I do B and then I do this orthogonal projection, that self-adjoint unbounded operator should be contained in first doing the projection onto H and then plugging that into B. So if H is reducing for B, then you can restrict B to H and you get an unbounded self-adjoint operator on H, and it's just literally B restricted to H. And the proposition you have to prove is that if you have a self-adjoint operator B on K, and you have a reducing subspace for H, and you happen to know that B has a spectral resolution P, then you can restrict P to H in a natural way to get a spectral resolution of the restriction B restricted to H. Namely, what does P restricted to H look like? What does it do to some measurable set omega? What projection is it? You take the projection P sub omega, you restrict it to H. Unfortunately, that may not give you values in H again, so then you have to follow that up with the projection onto H. You have to show that those are actually projections and that they actually are projection value measure, and they do give you a spectral resolution of B restricted to H, but none of it is terribly difficult. And that will be our main method for showing that an arbitrary self-adjoint operator on H has a spectral resolution. Using non-standard techniques, we'll find an extension to a larger space K from transfer and some extra arguments. We'll know that thing has a spectral resolution, and then we'll quote this restricting spectral resolutions proposition. Okay, the other basic technique we need in working with projection value measures is a push forward, just like you have push forwards of ordinary measures. So if I have a measurable map between measurable spaces and a projection valued measure on the first space, I can push it forward via this map to get a projection valued measure on the second space in the natural way. So what projection should it assign to some measurable set omega? It should just be the projection assigned by the inverse of omega under the measurable map phi. It's an sort of an obvious construction mimicking what you would do in ordinary measure spaces, yet surprisingly, I couldn't find much about this in the literature on projection value measures. But in any event, you can do it. And two basic facts from ordinary measure theory, you just check also work in this context. Namely, if I have this setup, a measurable map between measurable spaces, and a projection value measure on the first one, then I can look at the complex measure mu xy associated to P, or I could also look at the complex measure associated to the push forward, let's call it nu xy, and then those two are also related by phi as a push forward. So in other words, taking the scalar measures associated to a projection value measure and taking push forward, those two operations commute. And then the other fact is just a change of variables formula. So if I have a measurable function f on y, then I could ask, or I could consider the operator on h, which is the integral of f with respect to the push forward projection value measure. I could also consider the measurable function f compose phi on x and integrate it with respect to the original projection value measure. Those are the same unbounded operators on h. Okay. All right, so we're finally ready to discuss the non-standard approach to the theorem. Need to remind everyone, hopefully this is sort of familiar, but if it's not, just remind everyone about the non-standard Hull construction for Hilbert spaces. So we fix an internal Hilbert space H, and I set the finite points of H to be all those elements who have finite norm. If I look at the map, which takes a finite element to the standard part of its norm, that's a semi-norm on the finite elements, right? It's not necessarily a norm because you could have standard part norm 0, right? If your norm is an infinitesimal. So you fix that, you mod out by the monad of H, so all the finite vectors whose norm is an infinitesimal, and you get an honest norm space called the non-standard Hull, which is just, again, the finite points modulo the monad. And just use this circle notation that's quite popular. So if X is a finite point, its coset, its class in the non-standard Hull we'll call circle X. And the non-standard Hull is actually a Hilbert space. So first of all, it's an inner product space. So if I take two finite points, then by Cauchy-Schwarz, the inner product is finite again. And so I could take the standard part of that. Again, if that could be 0, but when you go down to equivalence classes, then you get an honest inner product that way. So if I take the inner product of circle X and circle Y and define that to be the standard part of the inner product of X and Y, that's well-defined independent of representatives, and it's an actual inner product. And a little saturation argument tells you that actually this inner product space is complete. So you have a Hilbert space, and it's called the non-standard Hull of the original internal Hilbert space H. Now, if I have a finitely bounded internal operator on H, what I mean by that is I have an internal linear operator, say B from H to H. And when I calculate its internal operator norm, if that's a finite element of star R, we call that finitely bounded. And finitely bounded internal operators, as you can easily check from the definition of operator norm, they must map finite elements to finite elements. And in fact, they give you a well-defined map on the non-standard Hull by sending circle X to circle of BX. Again, the finiteness of the operator norm tells you that if X and Y are infinitely close, then B of X and B of Y will also be infinitely close. And we call this the non-standard Hull of the operator B. Rob's main contribution to this is to give a notion of a non-standard Hull of B when B is not necessarily finitely bounded. It's just internally bounded, but not necessarily with a finite operator norm, assuming that B is also self-adjoint. We'll discuss that more in a second. But this is a very, I hate to say it, sort of standard, non-standard construction, this non-standard Hull of a finitely bounded internal operator. And it's easy to check that the standard operator norm of circle B is the standard part of the operator norm of B. The other thing that we'll need is a little bit of complex Loeb theory. For some reason, I couldn't find anything about this in the literature. It's kind of surprising. In any event, it's not too difficult. So let's suppose I have an internal finitely bounded complex measure, mu, on the algebra of internally Borel sets. And I calculate the internal Radon-Nikodym derivative, the derivative of the absolute value of mu with respect to mu. And let's call that H. Okay, then I'm going to define a standard complex measure. I'm going to call it d mu L, defined on the Loeb measurable subsets of R. So here, when I talk about the Loeb measurable subsets of R, I mean you start with the algebra of internally Borel sets and you do the Loeb measure construction. Then I'm going to define the standard complex measure d mu L by the equation d mu L should just be the standard part of H times the derivative of the Loeb measure associated to the absolute value of mu. Right? The absolute value of mu is a positive measure, so I can take the Loeb measure of that, that's some measure, and I'm going to multiply it by the standard part of H. Now I'm going to get a complex measure that I call d mu L, and I'll think of it as the Loeb measure of mu. So standard part of H makes sense, first of all, because by the definition of the Radon-Nikodym derivative, actually H of X will have modulus 1 for all X and omega, so that's not a problem. And it's pretty easy to check by this definition that the absolute value of mu L is the Loeb measure associated to the absolute value of mu. And to see that this is a good definition, just one checks the little equation here that the Loeb measure of omega, as I've defined it, so mu L of omega, is the standard part of the original measure of omega when omega is internally Borel. So on the original algebra. So this is a good notion of a Loeb measure. Okay, so with all that aside, we can now explain how you can define projection valued Loeb measures. So Rob describes this in a slightly different way in his paper, but I find this description a little more intuitive. Okay, so what is a projection valued Loeb measure? We start with the assumption that I have an internal Hilbert space H and an internal projection valued measure on the algebra of internally Borel subsets of R. So just to be clear, what do I mean by that? I mean, first of all, for every internally Borel set omega, P sub omega is an internal projection on H. P sub empty set is 0, and P sub star R is the identity of H. And P is merely finitely additive. So if I have finitely many internally Borel sets, omega 1 through omega n, that are pairwise disjoint, and I call their union omega, then P sub omega on an element X in our internal Hilbert space is just the sum of the P sub omega IX. Now, internal projections are finitely bounded. They have internal norm 1, in fact. You can consider their non-standard hulls, circle P. Those are bounded operators on the non-standard hull. And in fact, you can check they're actually projections on the non-standard hull. Okay, and just like before, each pair of vectors xy give us an internal complex measure, mu xy, on the internally Borel sets, and using the exact same formula. And by transfer, they are actually finitely bounded measures because the total variation is at most, again, the product of the norms of X and Y, and those are finite hyperreals because X and Y are finite elements of H. But now, if you calculate this complex Loeb measure that we defined, mu xy L of omega, so mu xy is this internal complex measure, so we defined a Loeb measure for it 2 slides ago. And we calculated that it does what it should on the original internal algebra, in this case, the internally Borel sets. It's just the standard part of the original measure on omega. But that measure, once again, is defined to be the inner product of Y with P omega X. And that is the formula for the inner product on the non-standard hull. that's the inner product of circle Y, with the non-standard hull of P omega applied to circle X. So that's an equation that makes sense for internally Borel sets, but this Loeb measure is defined on all Loeb measurable sets. So maybe we could see if we can define circle P omega, not just for Borel, internally Borel sets, but actually all Loeb measurable sets. One hint that this could work is to look at the following formula. If I look at now mu x, remember mu x is short for mu xx, and that's a positive measure. So if I look at mu x L of omega, and that's the ordinary Loeb measure construction on this positive measure on omega, it's the supremum of the Loeb measure mu xl of omega prime, where omega prime is over all internally Borel subsets of omega, right? This is a standard approximation property of Loeb measurable sets. We have that formula for mu xl omega prime when omega prime is internally Borel. And then you can move that supremum into the inner product, where now the supremum is calculated in the lattice of projections. So that's the supremum over omega prime, circle P omega prime. That supremum is a supremum of projections. So you look at that formula right there, and that suggests maybe how you should define circle P omega for omega, a Loeb measurable set. We will define it to be the supremum over all internally Borel subsets omega prime of omega, circle P omega prime. And then by that calculation, you have that mu xl of omega for omega and a Loeb measurable set, once again has this nice formula for it. And then a standard polarization trick actually allows you to not just get that for mu x, but actually for mu xy, for any pair xy, and any Loeb measurable set omega. So we have this nice formula now for the Loeb measure of, so mu xyl, the Loeb measure of the complex measure mu xy, applied to omega, as related to now operators circle P omega, defined for all Loeb measures. And you can check that these circle P omegas are actually projections. Well, actually, sorry, that's just clear from the definition. But what's more important is you have a projection valued measure now, circle P, from the Loeb measurable subsets of R to the projections on this non-standard hull of H. This is essentially due to Rob. I just cleaned up some of the details. Okay, great. Now, armed with that, we can define the non-standard hull for internally bounded self-adjoint operators, slightly differently from how Rob did, but essentially equivalently. So what are we assuming now? We're assuming B is an internally bounded, but not necessarily finitely bounded. That's the key. It's just an a priori internally bounded self-adjoint operator on some Hilbert space H. And for some reason, we know that it has an internal spectral resolution. We just described the projection valued measure associated to this internal spectral resolution. So it's an honest now projection valued measure, circle P, defined on the Loeb measurable sets, and it takes values now as projections on the non-standard hull. Okay, what's bad about this is it's a projection valued measure not on the Borel subsets of the reals, but on the Loeb measurable subsets of the hyperreals. What we're going to do now is something analogous to my favorite construction of Lebesgue measure, something we're all probably familiar with. If you take the Loeb measure associated to hyperfinite counting measure on, let's say, an interval a hyperfinite set 0, 1 over n, 2 over n, 3 over n, etc., up through n over n, where n is infinite. And if you push forward Loeb measure onto 0, 1 using the standard part map, you get Lebesgue measure. We're going to do something very similar here. So we're going to push forward this projection valued measure, circle P, but with respect to what I'll call bold standard part. So I want the standard part map to be defined on all of star R. So if X is finite, you just do the standard part. If it's not finite, you just do 0, okay? And I'm gonna push forward the projection valued measure circle P by this bold standard part map. I'm now gonna get a projection valued measure on the Borel subsets of R to bounded operators on circle H. I'm gonna call this push forward projection valued measure Q. And when you integrate the identity function on the reals with respect to this push forward measure, which now makes sense because it's a projection valued measure on the Borel subsets of the reals, you get a operator, an unbounded self-adjoint operator on circle H, and we'll call that the non-standard hull of B. And to know that this is a good definition, you actually check, and I carry out the details in the paper, that this agrees with the usual definition of non-standard hull if B happens to be finitely bounded. Of course, in that case, you're assuming B has an internal spectral resolution by transfer of the spectral theorem for bounded self-adjoint operators, which we do not want to assume in proving our theorem. So when I say this, you look at this fact here, I'm saying if you assume B is finitely bounded and you know it has an internal spectral resolution, then this construction will agree with the much simpler construction of the non-standard hull in this special case. Okay, so once again, here's the definition of the non-standard hull of B. It's just the integral of the identity operator with respect to the projection value measure Q. By the change of variables formula, alternatively, you can think of this as the integral of bold standard part with respect to the projection valued measure circle P, which is defined on the Loeb measurable subsets of star R. And that's actually Rob's original definition. Although checking that those two are the same, he sort of just states it, but it takes a little bit of work to check for the same. And the following lemma is really the key fact we need to know about this construction. And Rob states it without proof, but it took us a little bit of a couple pages to prove it carefully. And namely, it says if X and BX are both finite, then first of all, circle X does belong to the domain of this operator, circle B. And moreover, when you calculate circle B of circle X, unfortunately, it's not as clean as just saying circle BX like it is in the finitely bounded situation. What it is, you take circle BX and then you plug it in to the projection associated with the Loeb measurable set, which is the finite subset, the finite part of star R. Right, the finite part of star R is not internal, but it is Loeb measurable. And so you do have a projection corresponding to it. So you have to plug circle BX into that projection, and now you have an equality. All right, now we're actually ready to give the proof of the spectral theorem. So first, let's suppose I have a symmetric, just simply a symmetric operator A on H. And it's a very easy overflow argument to get a nice hyperfinite approximation to the domain of A. What do I mean by that? I mean, we can find a hyperfinite dimensional subspace of star H sitting in between the domain of A and the non-standard extension of the domain of A. Okay, so what do I do now? I take my original operator A. Its non-standard extension is defined on star D of A. I just restrict to H. That's an operator now whose domain is H, but unfortunately, the values may not land in regular H again. So I follow it up with the internal projection onto regular H. And now I do have an operator from H to H. It's actually pretty easy to see that it's symmetric. It's symmetric and it's defined on all of bold H, regular H. So by transfer, it actually must be internally bounded and self-adjoint. We had this remark early on in the talk that if you have a symmetric operator who happens to be defined everywhere, then it must actually be bounded and self-adjoint. So we're transferring that fact. Okay, but now it is a bounded, so I guess the bounded is not really important because H here is hyper finite dimensional. So bounded is sort of internally bounded is automatic, but self-adjoint is the most important part. So we have this self-adjoint operator on this hyper finite dimensional space. So I can quote the finite dimensional spectral theorem and transfer to conclude that AH has an internal spectral resolution, which is the very first slide of the talk I explained. So I can calculate the non-standard hull of AH with respect to that internal spectral resolution, as I described on the previous slide. And then the theorem you have to prove is that this non-standard hull of AH, which is defined on the non-standard hull of H, is actually an extension of the operator, the original operator A, which is just defined on the domain of A. So you have to check a very tiny thing, namely the domain of A is contained in the domain of A is contained in the non-standard hull of H. Okay, so normally this is sort of would be an obvious thing, but in this unbounded context, there's a little bit of work to check. But in any event, this operator AH, which we think of as the hyperfinite dimensional approximation of this A, when you take its non-standard hull, it actually is an extension of A. Okay, so just reminding you of that. Okay, and then you have to make a small argument that the original standard space H, curly H, is reducing for this operator circle AH. And then when you take the restriction of circle AH to cal H, you get your original operator back. And now you quote our restricting spectral resolutions proposition. Circle AH has a spectral resolution, basically by definition, right? Circle AH was defined by its spectral resolution. So the restriction has one by that lemma, and the restriction is precisely the original operator A, who we were trying to show had a spectral resolution. All right, and that completes the proof. In the paper, I do this first in the bounded case where the details are easier, just to give an idea. But I want to stress the proof for the unbounded case does not rely on the bounded case. It simply relied on the finite dimensional case. Okay, so let me just end with some references. The second reference is where you can find this paper. The third reference is Moore's original proof in the bounded case. The last reference is Rob's paper where he introduces all this and explains how you can then try to do quantum mechanics in this formalism. And just as a fun reference, the first one, my colleague Jeff Barrett here in Irvine in the Logic and Philosophy of Science department is an expert in the foundations of quantum mechanics. And together we use this formalism to describe the so-called many worlds or Everettian approach to quantum mechanics using non-standard analysis to handle the case when you have a continuous spectrum, which is something that people in the many worlds camp often tend to not discuss because there wasn't really a good approach to the many worlds foundations when you have continuous spectra. And this non-standard approach here that we've discussed ends up being a nice approach. And so we wrote this paper about that in case you're interested. All right, well, thank you very much for watching, and I hope everyone enjoys the conference in Pisa. Wish I could be there, and I hope to see you all soon. Stay safe.